Welcome back, ladies and gentlemen. We're going to pick up our next topic for biochemistry, and that is talking about one of the most important compounds here on Earth, at least as far as it relates to living things, and that's water. So why is water so important? Well, first off, let's sort of just talk about water in general, right? So its connection to living things. Organisms are made mostly of water. Alright, you in fact are something like 97% water by content. We live in an environment dominated by water. We've got lakes and streams and rivers, and most of the Earth itself is covered in water via the oceans. And more than any other substance, organisms need water to survive. You can go a week, maybe more, without food, but you're not making it more than 24, maybe 48 hours if you're lucky, without water. When we get to evolution, we'll talk about how life really began in water, and that whole process of evolution initially took place surrounded by this crazy molecule called water. Part of why you need water more than any other substance is because all of your metabolic processes, right, those chemical reactions that make you function on a day-to-day basis, require water as part of that chemical process. And of all the other common substances on Earth, water is the only one that commonly exists in all three states somewhere on Earth at any given point in time, right? So liquid in the ocean, solids in our ice caps, water vapor in the air at all times. So our whole purpose for this particular section is to walk through what water is and what are the properties that are really important for sustaining life as it is. And so here's just sort of a list of what we're going to talk about. We'll start going over just the fact that water is polar and why it can hydrogen bond, and then those two pieces are really going to set the stage for us to be able to talk about cohesion, adhesion, everything else that's in this list. So let's start off with the fact that water is a polar molecule. And if you remember from our last section, we were talking about covalent bonding, right? And so covalent bonding means that I've got one or more atoms that come together to make a molecule, and in order to do that, they have to share those electrons. Why are they doing that? Because the whole goal is to get that full valence shell, whether we're talking about, in the case of something like these two hydrogen molecules here in the picture, they only need 2 electrons in their valence shell to be full. Alright, because remember they're in that top row of the periodic table, but everybody else below that then is going to ultimately be striving for that octet or 8 electrons in their valence shell. So, how do we achieve that? Well, we had a couple of options, and covalent bonding was one of them, by sharing those electrons, or we could do the ionic bonding, where one atom is going to give up electrons, somebody else is going to take them. But when we were talking about that sharing, okay, remember that we discussed the fact that not every atom shares electrons equally. So it may not give or take, it may not be an ionic situation, but that sharing still isn't universal, okay? So that those electrons aren't spending the same amount of time around every nucleus in the atoms of the molecule, atoms that are present in that molecule, in which case we end up with a polar covalent situation. So that's what we're dealing with in the case of water. So here is water in and of itself. Alright, oxygen naturally has 6 valence electrons. Each hydrogen has 1, and so here are my shared pairs of electrons. Oxygen now has the 8 it wants, and each hydrogen now has the 2 that it needs. But the big difference here is that oxygen atom is sucking those electrons towards itself so much more of the time because it's got such a higher electronegativity. It's a lot larger atom compared to these two hydrogens. And so we end up with that partial negative charge. Remember I said to you in that last PowerPoint, I'm going to be a stickler and make sure that you're including that partial, all right, to fully show and demonstrate your understanding that this is a partial charge. Oxygen's not fully taking on those electrons, it's just that they're hanging out there a little bit more of the time. Hydrogen doesn't get to keep them nearly as often, and so they end up with that partial positive. And a lot of times when you see molecules like this, they end up getting this bent shape because those partial charges are present. And that's typical of a water molecule in and of itself. Okay, so let's delve into water in and of itself, right? So I've got these two covalent bonds that are going on here. They're not equal sharing, and so as a result, I get a polar molecule, so partial positive versus partial negative over here. Electrons are spending a little bit more time around oxygen because of its higher electronegativity. Alright, but they are still sharing electrons, and so they're still covalent. But if I take a look at a water molecule as a whole, by the way, the actual entire molecule itself doesn't have a charge, right? It's just regions on that molecule that have these partial charges. And the reasoning for that is because I've got this partial positive here on this hydrogen. It gets canceled out by that partial negative from the electron that it's sharing over here. So these guys cancel out. Partial positive on this hydrogen also gets canceled out by the partial negative over here from the shared electrons here. So overall, a water molecule itself is technically neutral, but those regions of partial charge are going to become important because they are going to set us up for the ability for some intermolecular attractions, things we'll talk about as hydrogen bonds in just a moment, to be possible. Speaking of, here are your hydrogen bonds. So this is a type of intermolecular attraction, so between molecules, as opposed to intra, with an A, molecular, which would be between atoms in a molecule itself. So hydrogen bonds are intermolecular. They're considerably weaker. Okay, so if we go back to that idea of bond energy that we talked about at the end of the last section, hydrogen bonding is the weakest of the types of bonds that we're going to talk about this year. And so that's going to become important, but just because they're weak doesn't mean that there isn't some energy that's associated with them as opposed to if they didn't exist at all. So we often end up seeing diagrams of water molecules, or really any molecule that has a hydrogen with a partial charge is capable of hydrogen bonding with another molecule that's got a partial negative. And so we represent those hydrogen bonds usually with these dashed lines. Okay. And this hydrogen bonding is really what's going to set us up for all of the other water properties that we're going to be talking about. Now, I've got one thing I want us to go into your notes and add to this picture. Alright, although they've got the positives and negatives here, I want you to go through and add those little partial symbols. Alright, just so we really get into that habit of making sure we include those partial charges so that we know we're looking at a polar covalent bond as opposed to an ionic one. So if you need to take a second and pause the video to do that, do so, but make sure that you add those partial charge symbols to all of these guys here so we make sure we get in that habit. Alright, so let's start talking about some of our water properties, and let's start with two of the probably more simplistic ones that we've got out there, cohesion and adhesion. And these guys are going on all the time, not only with water, but there's lots of other molecules that exhibit these particular properties as well. So cohesion in and of itself, tendency of molecules of the same type to stick together. So water, whenever you see those beads beating up or those droplets of water, we're talking about water being cohesive with itself. Alright, but water's not the only thing that can cling to itself. Here is an example of some mercury. This is a particularly high cohesive material, and so it will definitely bubble up and stick together. Adhesion, on the other hand, is the attraction between unlike molecules. So two molecules that are now sticking together, but they are not the same substance. So think of something like your meniscus in a test tube. All right. And so water is adhesively connected to the glass itself. In fact, in this particular situation, we stick water into a test tube, and that adhesive attraction is actually slightly stronger between the water and the glass molecule than it is between the cohesive property of the water connecting to itself, and that's why you get this meniscus that looks like this. Alright, if I were to get a meniscus that actually bubbled up, and there are certain substances, stick them in a test tube, they'll do this, now you've got a stronger cohesive force. It's more sticking to itself than it is adhesively sticking to the glass. And if you ever get a meniscus where it goes completely flat, then the difference between the cohesive and adhesive forces are actually equal. And that's what you get that flat line from. Not a bad side note for yourself, by the way, right? So if it's curved down like this guy, more adhesion than cohesion, bubble up, more cohesion than adhesion, and straight across, that adhesion and cohesion are actually equal. So why do these properties matter in terms of living things? And this is something that as you're studying, not only should you be able to tell me what the definitions are and be able to explain the properties themselves, but really at the end of the day, we're talking about it from a biological standpoint, so why does it matter in terms of living things? Well, one of the biggest things that matters in terms of adhesion and cohesion to living things really is the combination of the two working together via something called capillary action. So capillary action is the ability of liquids to flow through these narrow tubes in the opposite direction of gravity. Why does capillary action matter to living things? Well, there's a whole host of reasons. One of the biggest ones that we can talk about, and one of the most classic examples that tends to show up in test questions and textbooks, has to do with why trees are able to be as tall as they are, alright, and still get the water that they need, which they're typically supplying from their roots, all the way up to the top of the tree itself. So how does this work? Well, here's my tree, alright, here are my roots, here's where the vast majority of the water is going to come from. We're going to suck it up, and it's going to come up through the trunk into the branches and then ultimately into the leaves. That's where most of that water really is getting used on a day-to-day basis. So how does it work? Well, I've got these series of conducting water cells. Think of them like veins like you have in your body, or arteries, blood vessels. It's very much a similar idea. These really thin tubes that stretch down here from the roots all the way up and into the leaves themselves. And so what ends up happening is that you get these really thin tubes, and in there I get these line of water molecules. Alright, and they'll literally stack themselves one on top of the other. So what I get is this adhesive force between that water and the cells that are lining these tubes. So that's going to help them prevent them from falling all back down against gravity, but at the same time, those water molecules are also cohesively connected to each other, and that's going to become important with how they get from here up to here in the first place. So the adhesion just kind of keeps them from falling back against gravity once they're in this linear arrangement. The cohesion is going to be important for how they get in that line in the first place. So if you've ever seen a Pez dispenser, right? Pez candy, you got that little character on the top, you stack all of your Pez one underneath the next, pull the head back, pull out the candy, and the next one pops up in line. Well, that's kind of what this water is doing here. Okay? So I get to the top of this leaf, and what process is happening here? Well, that water is warming up because it's being blown across by wind or interacting with the sun and the heat that gets produced thermally from there. And that water evaporates, right? We warm up that liquid water that's hanging out here in the roots and in the trunk and in the leaves, and we give it enough energy and it turns into a gaseous form and off it goes into the atmosphere, right? Process called transpiration. Hopefully that sounds familiar. If not a bad side note for yourself here as well. Alright. That evaporation of water specifically off a plant is called transpiration. So when that transpiration process happens, that water molecule that's now sitting here on this leaf, boop, pops off, alright, evaporates off into the atmosphere. But as it's doing that evaporation, it's using that cohesive force to yank the next guy up in line, just like that spring does in a Pez dispenser, popping the next candy up so that it's ready to be dispensed. And that's going to happen all the way down into the roots, where it's now going to suck in the next water molecule from the soil itself. And that process keeps happening, and that's what's going to feed all of the water from the roots all the way up into the leaves and then kind of back out. It's going to ultimately help keeping our water cycle functioning and cycling water as it's supposed to. Another combination, or where some of these properties come into play, is in surface tension. And while capillary action is an interplay between adhesion and cohesion, surface tension is really just strictly a cohesive property. And surface tension really is this ability to stretch a liquid at its surface without breaking it. So what's happening, well, here's my water, right? So all these little blue dots represent water molecules. These arrows, which you might want to label, this is cohesion going on. So when I'm down here under the depths of the water, I've got all of these cohesive interactions happening in pretty much a 360. Alright, in every direction I can think about. But when I get to the surface, all I've got up here is air, so no hydrogen bonding going on there. So no cohesion going on there. But I've got this linear progression of water molecules that are hydrogen bonding with each other, cohesively sticking to each other right here at the surface. That's what sort of creates this invisible film on the surface of a liquid that, at least for any organism who is capable of spreading themselves out without breaking through like this water strider, they can use that to their advantage. So you can see that they're curving that water, but they are able to spread out and distribute their weight enough that they don't go crashing straight through all of these hydrogen bonds, and so they can sit on the surface. It's a similar idea when we talk about buoyancy and being able to float. It's the same idea. How buoyant can you get yourself, or can we get a particular object that it's able to ride on top of those hydrogen bonds without busting through them? Alright, and so that's what's happening here at the surface. Water happens to have one of the greatest surface tensions of any liquid out there, and so that's why these little guys are able to hang out on top of the surface. It gives them an ecosystem to live in, and that's where it becomes important to them.